The history of pedestrian and suspension bridges is full of dramatic events. The first well-documented faulty footbridge was the Angers Bridge in France, which collapsed when French soldiers marched across it in step. 200 people died. The list of faulty bridges is long. The most famous example is that of the London Millennium Bridge, which began wobbling side to side on opening day in 2000 and had to be closed for repairs. Surprisingly, the wobbling occurred when the number of pedestrians exceeded a critical value of 165. The addition of one pedestrian caused the crowd to walk in step and the bridge to sway significantly. This phenomenon is poorly understood. Here at Georgia State University, we build computational crash tests for bridges, mathematical simulations of moving crowds and their interaction with the bridge. These crash test dummies can be used to test and predict instabilities. US code and industry standard bridge design tools don't consider crowd dynamics, which leads to faulty designs. We model the motion of a pedestrian's center of mass on the supporting leg falling sideways as a rigid upside-down pendulum. Newton's second law yields an equation for the acceleration side to side. When a pendulum swings, it's subject to gravity, elasticity, which controls the frequency of the oscillation, and damping, which reduces the amplitude. We extend this model to interaction with a vibrating platform, add various complexity to make the model more real and self-driven, and sum over the force of pedestrians to add the crowd. Until now, the prevailing theory has been that suspension bridges like the London Millennium Bridge wobble due to pedestrians falling in step with the bridge's oscillation. If you put several metronomes on a vibrating table, they will synchronize if they are at the same tempo. But humans don't walk like metronomes. They adapt their step. Our new research suggests that synchronization of the pedestrian's gait on such a bridge is not the cause of the bridge's vibration, but its consequence. The wobbling is due to negative damping, which occurs when pedestrians excite the bridge with a greater force than its natural damping. Synchrony then follows as pedestrians react to the bridge's vibration to maintain their balance, like passengers on a rocking boat. With mathematics, we can propose modifications to bridge designs that can make them much safer, preventing disaster.